All right, the interactions of radiant energy with atoms. Balmer's equation. Once again, looking at an experiment. And in order to do that, we once again want to make a couple observations. First of all, we want to define what a continuous spectrum is. At some point in your life, you've probably played with a prism. What happens when you shine white light through a prism, light from the sun through a prism? You break that light up and you get a rainbow. You see all the different colors and all the possible wavelengths. You see not just Roy G. Biv, but every color and wavelength in between. You see a complete set of continuous wavelengths within a certain range. That's what happens when you have white light. The reason we need to define this continuous spectrum is so that we can understand the significance of the work of a chemist named Balmer. What Balmer did was a very simple experiment, one that I hope to have video edited into this lecture shortly. But what happens in this experiment is Balmer took what Balmer did was he took some atoms and excited them. One of the easiest ways to excite an atom is to simply take a flame and throw the atom of your choice in there. Then look at the light given off by the atom. When Balmer did this, when he excited his atoms, what he noticed was that the light the atoms were given off was not a continuous spectrum. So observation. What Balmer observed was that when the light was given, the observation was when light was given off by the excited atoms, the energy was not a continuous spectrum. Instead of producing a continuous spectrum, the elements instead produced what are known as line spectrums. And what we see on this slide are actually a series of line spectrums. Sodium, for example, when excited, produced only a pair of lines within the yellow wavelength of the spectrum. Hydrogen, on the other hand, produced only 4 lines instead of a continuous spectrum. Why is this important? In order to understand why this is important, we have to understand where the light we're observing is coming from. When energy is added to this atom, that energy hits an electron. That electron becomes what's known as excited, meaning it moves to a higher energy state. Adding energy to an electron is like giving candy to a little kid. You give candy to a little kid, man, that kid gets excited. Just like an electron. He runs around, he races, he dashes, he moves. Half an hour later, what happens to the kid? Boom! He's face down in the carpet, butt up in the air, sound asleep. Same way for an electron. After it runs around for a while, it gets awfully tired, and it falls back down to a lower energy state. Well, energy can't be created or destroyed. So when the electron falls back down to a lower energy state, it emits some electromagnetic radiation. In other words, it emits some light. This is the light we see when we look at when we observe a line spectrum. It's this re-emitted light by the electron falling back to a lower energy state that we observe when we look at the line spectrum of an atom. Why is it important, then, that when we observe the energy given off by a falling electron, that we do not see a continuous spectrum? Here's why. If we had seen a continuous spectrum, in other words, if we'd seen a rainbow when we look at electrons falling down, then that would mean that an electron could have any energy state it wanted. But we don't see a rainbow. Instead, we see only certain set colors. That means that electrons can have only certain set energies within an atom. This was a mind-blowing concept. It had already been established that atoms had a nucleus, and it had already been established that the electrons moved around somewhere around the nucleus. But now, for the first time, we had experimental evidence that these electrons couldn't move around however they wanted to. They could only move around with certain set energies. This changed the face of chemistry forever. So, to summarize for the purpose of note-taking, when a prism is held up to white light, a continuous spectrum is emitted, which contains all the wavelengths of light. When atoms are heated, they produce a line spectrum, not a continuous spectrum. For example, if you were in class, I would actually run these two elements. If you heat up hydrogen in a vacuum tube, you get a discrete red color. If you look at that discrete red color through a prism, you see this spectrum over here. Not a continuous rainbow. See all those gaps? Neon over here, and yes, it's neon and that's sodium, but those were the examples and pictures provided to me by the book. Hopefully I'll correct that eventually on my own. But you don't see a continuous spectrum for that either. That means the following conclusions. 1. Electrons can't have any random energy inside an atom. Instead, electrons can have only certain set energies inside an atom. And then here's another conclusion that I think your book should have included but didn't. Are the line spectrum for sodium and hydrogen the same? No. So what does that mean about the energy of the electrons of sodium and hydrogen? Are they the same? No. the energies an electron can have are different for different elements. So Balmer was able to reach three really awesome and important conclusions. Like all good chemists, he wasn't satisfied simply by making a conclusion. He wanted to actually describe them mathematically. Balmer discovered that the inverse of the wavelength of the emitted light was equal to a constant times 1 over 2 squared minus 1 over n squared, where n was an element of the integers. In other words, n was a whole number. 1, 2, 3, 4, 5. Now what was odd was, let's not start with what's odd. Let's start with what this equation very elegantly and very simply signifies. This equation makes it very clear that we have an electron moving between an excited state and an unexcited state. What's interesting, however, is that in Balmer's equation, this bottom or low energy state is described with the integer 2. However, that's what the results showed of all of his experiments. Why was this? Well, Balmer was only using his naked eye to observe wavelengths. It turns out that there was an energy state lower than a 2, that there was a first energy state. However, the wavelengths that were emitted when electrons fell down to that first energy state, or n equals 1 state, lay outside the visible portion of the spectrum, and therefore Balmer wasn't able to see them. However, Reisenberg proved their existence and modified Balmer's formula to the form that we now use today. Reisenberg says that the inverse of the wavelength emitted as an electron moves between two energy states is equal to the difference of their multiplicative inverses squared times a constant. This constant, known as Reisenberg constant, also handles something else that was one of Balmer's experimental observations. Remember how he said that different elements, electrons can have different energy states? This constant is going to be different for every single element. Therefore, when we see R sub H, it means we're talking about a hydrogen atom or a hydrogen-like atom, meaning that we're just going to assume that the atom behaves like hydrogen. Therefore, this constant right here is only good for hydrogen-like atoms. If you were in my face-to-face class, I would give you this constant on all your exams. However, what was I going to say? However, it's not given to you in your online homework. You have to look it up. Therefore, if you're keeping a cheat sheet of formulas handy to use while you do homework, which is something I would always do, I would add not only this formula to it, but I'd add that constant to it as well. And that's it for this lecture.